Lecture 11, Hashing and Data Integrity. Theme, Data Integrity, Digital Signatures, and PKI. Technical University of Moldova. Lecturer, Maxim Masiutin, Associate Professor. Introduction. Hello, everyone. Welcome to Lecture 11. Today we explore cryptographic hash functions, arguably the most versatile tools in the cryptographer's toolkit. While encryption protects confidentiality and signatures prove authenticity, hash functions are the silent workhorses that make much of modern security possible. You encounter hash functions dozens of times every day, even if you do not realize it. When you log into a website, your password is verified using a hash. When your browser connects to a secure site, hashes verify the integrity of certificates. When you download software, you can verify it has not been tampered with using a hash. When you commit code to Git, each commit is identified by a hash. Today we will understand what makes a good cryptographic hash function, explore the major algorithms from MD5 through SHA-3 and BLAKE3, learn how to use hash functions for message authentication, and dive into the specialized world of password hashing where being slow is actually the goal. Part 1. Cryptographic Hash Function Fundamentals. What is a hash function? A cryptographic hash function takes an arbitrary amount of input data and produces a fixed-size output called the hash, digest, or fingerprint. This output is deterministic. The same input always produces the same output, yet appears completely random. For example, S.H.A-256 always produces a 256-bit, 32-byte output, whether you hash a single character or an entire movie file. The hash of hello will always be the same, but the hash of hello will be completely different. The hash function h applied to message m produces hash h, where m is the message of any length, and h is the hash of fixed length. Essential security properties. Cryptographic hash functions must satisfy 3 fundamental security properties. Understanding these properties is crucial for knowing when and how to use hash functions correctly. Preimage resistance, one-way property. Given a hash value h, it should be computationally infeasible to find any message m such that the hash of m equals h. Think of it this way. If I give you a hash, you should not be able to work backward to find what produced it. The only option should be trial and error. Hash random inputs until you find a match. For a 256-bit hash, this means trying an average of 2 to the power of 255 inputs, which is computationally impossible. Why does this matter? If you store password hashes, not passwords, an attacker who steals the hash database should not be able to recover the passwords. Second, preimage resistance. Given a message M1 and its hash h of M1, it should be computationally infeasible to find a different message M2 such that h of M2 equals h of M1. This is subtly different from preimage resistance. Here, the attacker knows both the original message and its hash, and tries to find a different message with the same hash. Why does this matter? If you sign a document by signing its hash, an attacker should not be able to create a different document with the same hash and claim you signed it. Collision resistance. It should be computationally infeasible to find any 2 different messages M1 and M2 such that the hash of M1 equals the hash of M2. Note that collisions must mathematically exist. We are mapping infinite possible inputs to a finite number of outputs, but finding them should be impractical. The birthday paradox makes collision finding easier than preimage attacks. For a hash with n-bit output, finding a collision requires approximately 2 to the power of n over 2 hash computations. This is why S.H.A-256 provides 128 bits of collision resistance, not 256 bits. The Avalanche Effect. A good hash function exhibits the Avalanche Effect. Changing a single bit of input changes approximately half the bits of output. The outputs appear statistically independent even for very similar inputs. For example, the S.H.A-256 hashes of test1 and test2 differ in about 130 bits out of 256, with no discernible pattern. This property is essential for security. Any pattern would give attackers information they could exploit. Merkle-Damgard Construction. Most classical hash functions, MD5, S.H.A-1, S.H.A-2, use the Merkle-Damgard construction. Pad the message to a multiple of the block size. Split into blocks. Process each block sequentially with a compression function. Each compression function takes the previous state and current block, producing new state. The final state is the hash. This construction has a mathematical property. If the compression function is collision-resistant, so is the overall hash function. However, it has weaknesses including length extension attacks, where knowing the hash of M allows computing the hash of M concatenated with padding concatenated with M prime without knowing M. Part 2. Deprecated hash functions. MD5, Message Digest 5. MD5 was designed by Ronald Rivest in 1991 to replace MD4. It produces a 128-bit hash and was widely used for over a decade. MD5's downfall came through progressive cryptanalytic attacks. 1996. Weaknesses in compression function discovered. 2004. First practical collision found by Wang et al. 2008. Chosen prefix collisions enabled rogue CA certificate creation. Today, collisions can be generated in seconds on a laptop. MD5 is completely broken for collision resistance. An attacker can create two different documents with the same MD5 hash. This was dramatically demonstrated in 2008 when researchers created a rogue SSL certificate by exploiting MD5 collisions. Current status: MD5 should never be used for any security purpose. It is acceptable only as a non-cryptographic checksum for accidental corruption detection, where no attacker is involved. S.H.A-1 Secure Hash Algorithm 1. S.H.A-1 was designed by the NSA and published by Ingesti in 1995. It produces a 160-bit hash and was the most widely used hash function for nearly 2 decades. S.H.A-1's decline was slower but inevitable. 2005. Theoretical collision attacks published. 2017. First practical collision, shattered attack by Google. Cost: approximately 110 GPU years. The shattered attack produced 2 different PDF files with identical S.H.A-1 hashes. These were not random data, but actual PDF documents that could display different content. Current status: S.H.A-1 is deprecated for all security applications. Major browsers reject S.H.A-1 certificates, and Git has begun transitioning away from S.H.A-1. Use SHA-256 or better for any new application. Part 3. The S.H.A-2 family. Overview. S.H.A-2, designed by the NSA and published in 2001, is actually a family of hash functions with different output sizes. S.H.A-224, 224-bit output, based on S.H.A-256. S.H.A-256, 256-bit output, most commonly used. S.H.A-384, 384-bit output, based on S.H.A-512. S.H.A-512, 512-bit output. S.H.A-512 over 224 and S.H.A-512 over 256. Truncated S.H.A-512. Despite coming from the same organization as S.H.A-1, S.H.A-2 uses a fundamentally different design and remains secure. No significant cryptographic weaknesses have been found in nearly 25 years of analysis. S.H.A-256. S.H.A-256 is the workhorse of modern cryptography. It operates on 512-bit blocks and maintains a 256-bit state through 64 rounds of mixing operations. Each round uses bitwise operations and or XOR not modular addition, right rotations. The algorithm uses a message schedule to expand each 512-bit block into 64 32-bit words, ensuring that every input bit affects many output bits. SHA-256 provides 256-bit preimage resistance, 256-bit second preimage resistance, 128-bit collision resistance, birthday bound. SHA-256 is used in TLS certificates, Bitcoin mining, HMAC constructions, digital signatures, and countless other applications. SHA-512 and Variants. SHA-512 operates on 1024-bit blocks and produces a 512-bit hash. It uses 80 rounds instead of 64 and operates on 64-bit words instead of 32-bit. On 64-bit processors, SHA-512 is often faster than SHA-256 because it processes more data per operation with the same number of instructions. This seems counterintuitive. The longer hash is faster, but makes sense given 64-bit CPU architecture. S.H.A-512 over 256 is S.H.A-512 truncated to 256 bits with different initialization values. It provides resistance to length extension attacks, unlike raw S.H.A-256, often faster than S.H.A-256 on 64-bit systems. Same effective security as S.H.A-256. S.H.A-384 is S.H.A-512 truncated to 384 bits, commonly used where more than 128 bits of collision resistance is needed. When to use S.H.A-2. S.H.A-256 remains the recommended hash function for most applications in 2025 to 2026. Digital signatures, certificate fingerprints, HMAC construction, key derivation with HKDF, general integrity verification. Use S.H.A-512 when running on 64-bit systems where it is faster. Need more than 128 bits of collision resistance. Protocol specifies it. Some TLS cipher suites. Part 4. S.H.A-3 Keccak. Background and competition. Even though S.H.A-2 was not broken, NSD was concerned about having all its standards come from one design family. If a fundamental weakness in the S.H.A-2 construction were discovered, there would be no fallback. In 2007, NSD announced a competition for S.H.A-3, similar to the AES competition. After 5 years of public cryptanalysis, the Keccak algorithm, pronounced Keccak, was selected in 2012 and standardized as S.H.A-3 in 2015. The sponge construction. S.H.A-3 uses a radically different construction called a sponge. Instead of Merkle-Damgard's sequential compression, initialize a state of 1,600 bits, 200 bytes. Absorbing phase. XOR input blocks into the state. Apply permutation after each. Squeezing phase. Extract output blocks from the state. Applying permutation between extractions. The state is divided into a rate, bits that interact with input and output, and a capacity, bits that provide security margin. The capacity determines security. SHA-3-256 has capacity of 512 bits, providing 256-bit security. S.H.A-3 Variants. The S.H.A-3 standard defines SHA-3-224, 224-bit output, 448-bit capacity. SHA-3-256, 256-bit output, 512-bit capacity. SHA-3-384, 384-bit output, 768-bit capacity. SHA-3-512, 512-bit output, 1024-bit capacity. These provide drop-in replacements for S.H.A-2 functions with equivalent security. SHAKE128 and SHAKE256. S.H.A-3 also defines extendable output functions, XOFs. SHAKE128, 128-bit security, arbitrary output length. SHAKE256, 256-bit security, arbitrary output length. Unlike fixed output hash functions, XOFs can produce as much output as needed. SHAKE128 with 256 bits of output is not the same as SHAKE128 with 512 bits. They start the same, but continue differently. XOFs are useful for key derivation, replace HKDF in some contexts, mask generation functions, deterministic random number generation, creating hash functions of custom sizes. S.H.A-3 versus S.H.A-2. When should you use S.H.A-3 versus S.H.A-2? Prefer S.H.A-2, S.H.A-256, S.H.A-512 when maximum compatibility is needed. Hardware acceleration, SHANI, is available. You need the fastest possible software performance. Prefer S.H.A-3 when length extension resistance is needed. S.H.A-3 is inherently immune. Diversity from S.H.A-2 is desired for defense in depth. Variable length output is needed. Use SHAKE. Side-channel resistance is important. Keccak's design helps. In practice, both S.H.A-2 and S.H.A-3 are excellent choices. The cryptographic community has analyzed both extensively, and both remain secure. Part 5. Blake 2 and Blake 3. Blake 2. Blake 2, published in 2012, is a hash function optimized for speed while maintaining security. It was based on Blake, a S.H.A-3 competition finalist, but redesigned for practical deployment. Blake 2 comes in two main variants. Blake 2B, optimized for 64-bit platforms, produces up to 512-bit hashes. Blake 2s, optimized for 32-bit platforms, produces up to 256-bit hashes. Key features: faster than MD5 in software. Yes, faster than the broken algorithm. Configurable output length. Built-in keying. Can act as a MAC without HMAC wrapper. Built-in personalization and salt. Tree hashing mode for parallel processing. Blake 2 is used in libsodium as the default hash function, WireGuard VPN, Argon 2 password hashing, many file verification tools. Blake 3. Blake 3, released in 2020, takes Blake 2's ideas further. Approximately 4 times faster than Blake 2. Parallelizable by design, uses a Merkle tree structure. Single algorithm works on all platforms, no separate B and S variants. Fixed 256-bit output, XOF mode for longer output. Built-in keyed hashing and key derivation. Blake 3 achieves its speed through reduced rounds, 7 versus Blake 2's 10 to 12. Tree structure enabling parallelism. SIMD-friendly operations. Blake 3 is excellent for high-speed file hashing, large data verification, applications that can use parallelism, replacing MD5 or S.H.A-1 in non-cryptographic checksums. Comparison summary. S.H.A-256 has excellent security, good speed, sequential processing, and is used for standards compliance. S.H.A-512 has excellent security, good speed on 64-bit systems, and also uses sequential processing. SHA-3-256 has excellent security, moderate speed, sequential processing, and provides diversity from S.H.A-2. Blake 2B has excellent security, very fast speed, limited parallelism, and is good for general-purpose use. Blake 3 has excellent security, extremely fast speed with full parallelism, and is best for high-speed hashing. Part 6. Message Authentication Codes. Hash functions verify integrity. Has the data changed? But they do not verify authenticity. Did the data come from who we think? A message authentication code, MAC, provides both. HMAC, hash-based MAC. HMAC, standardized in RFC 2104, constructs MAC from any cryptographic hash function. The formula is HMAC of K and M equals the hash of K XORed with the outer pad. concatenated with the hash of K XORed with the inner pad concatenated with the message M, where K is the secret key, padded to block size. OPAD and IPAD are fixed constants. The double hashing structure provides security even if the underlying hash has some weaknesses. HMA.C. MD5 is actually still considered secure for authentication, though not recommended for new applications. Common instantiations. HMA.C. SHA-256. Most widely used. 256-bit output. HMA.C. SHA-384. Used when 128-plus-bit security is needed. HMA.C. SHA-512. Maximum security. HMAC is used in TLS for record authentication. API authentication. HMA.C. SHA-256 signatures. JWT, JSON Web Tokens. HKDF, key derivation. KMAC, Keccak MAC. S.H.A-3 sponge construction allows direct key absorption without the HMAC wrapper. KMAC, standardized in NEST ESP 800-185, provides a MAC directly from Keccak. KMAC advantages. Single pass versus HMAC's double hashing. Built-in domain separation. Variable output length, XOF mode. KMAC is specified in KMAC 128, 128-bit security. KMAC 256, 256-bit security. KMAC is newer and less widely deployed than HMAC, but is becoming more common in systems already using S.H.A-3. Poly 1305. Poly 1305, designed by Daniel Bernstein, is a one-time authenticator used with SHA-20, SHA-20 Poly 1305, and A.E.S, G.C.M. Uses GASH, but Poly 1305 is available as alternative. Key properties. Extremely fast, especially in software. Produces 128-bit tag. Requires a new key for every message, typically derived from cipher. Information theoretically secure for single use. Poly 1305 is not used standalone, but as part of authenticated encryption constructions. SHA-20 Poly 1305 derives a Poly 1305 key from the encryption key and nonce for each message. When to use what? HMA.C. SHA-256. Default choice. Maximum compatibility. HMA.C. SHA-512. When speed matters on 64-bit systems. KMAC 256. When already using S.H.A-3. Want XOF features. Poly 1305. As part of authenticated encryption, SHA-20 Poly 1305. Never use. Unkeyed hash for authentication, anyone can recompute. HMAC with MD5 or S.H.A-1 for new applications. Custom MAC constructions. Part 7. Password hashing. Password hashing is fundamentally different from general-purpose hashing. For file integrity, we want fast hashes. For passwords, we want slow hashes. The password hashing problem. When users create passwords, they choose poorly. Studies consistently show that most passwords come from a relatively small set. Dictionary words with simple modifications. Keyboard patterns, QWERTY, 1, 2, 3, 4, 5, 6. Personal information, names, dates. Previously leaked passwords. An attacker with a hash database will try these common passwords first. With fast hashes like S.H.A-256, an attacker can try billions of passwords per second on consumer hardware. Even a moderately complex password falls quickly. The solution is deliberately slow hash functions that make brute force attacks expensive. Password hashing requirements. A good password hash function must be slow, configurable work factor to keep pace with hardware. Use memory. Prevent GPU and ASIC acceleration. Use SALT. Prevent rainbow tables and multi-target attacks. Be deterministic. Same password must verify consistently. bcrypt. bcrypt, published in 1999, was designed specifically for password hashing. It is based on the Blowfish cipher's expensive key setup. Key features. Configurable cost factor. 2 to the power of cost iterations. 128-bit salt embedded in output. 184-bit hash output. Maximum password length of 72 bytes. The bcrypt format is $2b, cost value, then the salt and hash value. Example, $2b, $12, then salt of 22 characters followed by hash of 31 characters. Bcrypt remains secure and widely used. However, it has limitations. 72-byte password limit. Does not utilize memory, GPU attackable. Cost factor only affects CPU time. SHA-2. SHA-2, published in 2009, adds memory hardness to the password hashing problem. It is designed to be expensive in both CPU time and memory. Parameters. N. CPU and memory cost. Iterations must be power of 2. R. Block size, memory usage multiplier. P. Parallelism factor. SHA-2 uses memory deliberately. The algorithm must keep a large array in memory and access it randomly. This makes GPU attacks expensive because GPUs have limited memory per core. SHA-2 is used by cryptocurrency mining, Litecoin, Dogecoin, encrypted file systems, password vaults. Argon 2. Argon 2, winner of the password hashing competition in 2015, is the current state-of-the-art. It was designed to address limitations in both bcrypt and SHA-2. 3 variants. Argon 2D, data-dependent memory access, fastest, used for backend only. Argon 2I, data-independent memory access, side-channel resistant. Argon 2ID, hybrid of D and I, recommended for most uses. Parameters. T. Time cost, iterations. M. Memory cost, kilobytes. P. Parallelism, threads. Argon 2 advantages. Memory hard, like SHA-2. Configurable time, memory, and parallelism independently. Side-channel resistant variant. Argon 2I, Argon 2ID. No password length limit. IETF standardized, RFC 9106. Recommended Argon 2 ID parameters, 2025. Minimum, M equals 47104, 46 MB, T equals 1, P equals 1. Interactive logins, M equals 65536, 64 MB, T equals 3, P equals 4. High security, M equals 2097152, 2 GB, T equals 1, P equals 4. Password hashing best practices. Always use a dedicated password hashing function. Argon 2ID, bcrypt, SHA-2. Never use general-purpose hashes. SHA-256 alone is not suitable. Always include salt. All modern password hashers do this automatically. Tune parameters for your hardware. Target 100 ms. 1s for interactive logins. Increase cost factors over time. Hardware gets faster. Use constant time comparison. Prevent timing attacks. Implement rate limiting. Prevent online brute force. Password hash migration. If your system uses old password hashing, MD5, S.H.A-1, weak bcrypt. Option 1. Wrap existing hashes. The new hash equals Argon 2 ID applied to the old hash. Verify. Compute old hash, then Argon 2 ID. On next login, upgrade to Argon 2 ID applied directly to the password. Option 2. Force password reset. More disruptive but cleaner. Appropriate for high-security systems. Option 3. Gradual migration. Hash new and changed passwords with Argon 2 ID. Upgrade existing users on login. Eventually force remaining users to reset. Part 8. Practical applications. File integrity verification. Hash functions verify that files have not been modified. To verify file integrity, you run the SHA-256 some command on the file, saving the hash to a checksum file. Later, you run SHA-256 some with the check flag to verify the file still matches. For software distribution, publisher computes hash of release. Hash signed with publisher's key. Users download file and verify hash matches. Git Commit Identification. Git uses S.H.A-1, transitioning to S.H.A-256 to identify. every file, blob, every directory, tree, every commit. The commit hash depends on tree hash, directory structure, parent commit hashes, author and committer information, commit message, timestamp. Any change to any part of history changes all subsequent hashes. This is what makes Git history tamper evident. Proof of work, blockchain. Cryptocurrencies use hash functions for proof of work. Find nonce such that the hash of the block concatenated with the nonce starts with many zeros. Requires many hash computations, mining. Verifying is cheap, single hash. Bitcoin uses double S.H.A-256, meaning S.H.A-256 applied to the S.H.A-256 hash of the block. Content-Addressable Storage. Systems like IPFS use hashes as content identifiers. CID equals hash of content. Same content always has same CID. Content can be verified against its CID. Enables deduplication and integrity verification. Commitment schemes. Hash functions enable cryptographic commitments. Commit phase. Send the hash of the secret concatenated with the knots. Reveal phase. Send secret and knots. Verify. Check hash matches. This is used in sealed bit auctions, voting protocols, fair random number generation. Part 9. Best Practices Summary. Algorithm selection. For general purpose hashing. Default. S.H.A-256. High security. S.H.A-384 or S.H.A-512. Speed critical. Blake 3 or Blake 2B. S.H.A-3 ecosystem. SHA-3-256. For Macs. Default. HMAC. SHA-256. With S.H.A-3 KMAC 256. Authenticated encryption. Use the mode's built-in MAC. For passwords. Default. Argon 2 ID. Legacy compatibility. bcrypt. Never. Plain S.H.A-256. MD5. S.H.A-1. Never do. Never use MD5 or S.H.A-1 for any security purpose. Never use plain hashes for passwords. Never use hash for authentication without a key. Use HMAC. Never implement your own hash function. Never truncate hashes below the birthday bound. Never ignore timing attacks in hash comparison. Implementation notes. Use cryptographic libraries, not custom implementations. Use constant time comparison for MAC verification. Include protocol version and domain separation in inputs. Consider hash algorithm agility in protocol design. Monitor for deprecation announcements. Conclusion. Today we explored the world of cryptographic hash functions, from the fundamental properties that make them secure to the modern algorithms that protect our digital infrastructure. Key takeaways. Hash functions provide integrity, not authenticity. Use HMAC for authentication. MD5 and S.H.A-1 are broken for collision resistance and should not be used for security. S.H.A-256 is the standard, widely deployed, well-analyzed, secure. S.H.A-3 provides diversity from S.H.A-2 with different construction. Blake 2 and Blake 3 offer speed for applications where performance matters. Password hashing is special. Use Argon 2 ID, bcrypt, or scrypt, never general-purpose hashes. The avalanche effect and collision resistance are what make hash functions useful for security. Next week, we bring together everything we have learned about hashing, symmetric encryption, and asymmetric cryptography to explore digital signatures and public key infrastructure, how we authenticate identity in the digital world. Discussion questions. What are the consequences of organizations still using deprecated hash functions like MD5 and S.H.A-1 in their systems? How should organizations approach migrating password storage from older hashing methods to modern algorithms like Argon 2 ID? What role do hash functions play in blockchain technology, and what are the security implications? Thank you for your attention. See you next week. Review questions. List the 3 essential security properties of cryptographic hash functions and explain each. Why are MD5 and SHA-1 considered broken for security purposes? What attacks have been demonstrated? Compare the Merkle-Damgard Construction SHA-2 with the Sponge Construction SHA-3. What is HMAC, and how does it differ from simply prepending a key to a message before hashing? Compare BLAKE2 and BLAKE3 with SHA-256 in terms of speed and security. Explain why general-purpose hash functions are unsuitable for password hashing. Describe Argon 2 ID and explain why it is recommended over bcrypt and PBKDF2 for password hashing. What is a length extension attack, and which hash constructions are vulnerable to it? Key terms. Argon 2 ID, a memory-hard password hashing algorithm, winner of the password hashing competition. Avalanche Effect, a property where small input changes cause dramatic output changes. bcrypt, a password hashing function based on the Blowfish cipher. Birthday Attack, a cryptographic attack that exploits probability mathematics to find hash collisions faster than brute force. BLAKE2, a fast cryptographic hash function faster than MD5 while remaining secure. BLAKE3, a parallelizable hash function derived from BLAKE2, offering extreme speed. Collision resistance, the property that it is computationally infeasible to find two inputs producing the same hash. Hash function, a function that maps input of arbitrary size to fixed size output. HMAC, hash-based message authentication code, providing both integrity and authenticity. KMAC, Keccak Message Authentication Code, a MAC based on the SHA-3 family. MD5, Message Digest 5, a broken hash function that should not be used for security. Merkle-Damgard, a construction used by MD5, S.H.A-1, and S.H.A-2 family hash functions. Password hashing, using deliberately slow hash functions to protect stored passwords. Pre-image resistance, the property that given a hash, it is infeasible to find the original input. SALT, random data added to input before hashing to prevent rainbow table attacks. scrypt, a memory-hard password hashing function designed to be resistant to hardware brute force attacks. S.H.A-1, Secure Hash Algorithm 1, broken for collision resistance since 2017. S.H.A-256, a member of the S.H.A-2 family producing 256-bit hashes, widely used and secure. S.H.A-3, the third-generation secure hash algorithm based on the Keccak Sponge Construction. SHAKE and XOF, S.H.A-3 extendable output functions, SHAKE128, SHAKE256, that produce variable length hash outputs. Sponge Construction, the construction underlying S.H.A-3, resistant to length extension attacks. References and further reading. NIST FIPS 180-4, Secure Hash Standard, S.H.A-1, S.H.A-2 family. NIST FIPS 202, S.H.A-3 standard. NIST SP 800-185, S.H.A-3 derived functions, KMAC, C-Shake. RFC 2104, HMAC, heat hashing for message authentication. RFC 9106, Argon 2 memory hard function for password hashing. BLAKE2 paper. BLAKE2, simpler, smaller, fast as MD5. BLAKE3 paper. BLAKE3, one function, fast everywhere. Password hashing competition, 2015 winner. Argon 2. Wang et al. Finding collisions in the full S.H.A-1, 2005. Stevens et al. The first collision for full S.H.A-1, 2017.